In this video, we are going to practice finding Bronsted-Lowry acids and Bronsted-Lowry bases. So a Bronsted-Lowry acid donates protons and a Bronsted-Lowry base accepts protons. So what we have to look at is the products in respect to the reactants. So if I look at this product, I negative, I have to try and figure out where it came from. Obviously, it didn't come from the H2O, so it must have come from this hydroiodic acid. So because it came from this hydroiodic acid, when I compare these two things, this iodine is short a hydrogen, which means that this HI donated a proton. It got rid of its hydrogen. Remember, protons are H+. So this got rid of its H+, it got rid of its proton, so that means that it's donating it. That makes this an acid. Since this H2O is the only other thing in this equation, it has to be the base, but if I want to look at that first, that's fine too. So if I compare H2O to H3O+, it's increased by one proton. H3 is larger than H2, plus it has this positive charge, and that's an indicator to me that it gained a proton. So if this gains a proton, if it accepts a proton, this is a base. In the next problem, this is just the reverse of what happened before. If I look at I negative and I compare it to this over here, I negative versus H negative. These are the two things that I'm comparing. So this I negative gained a proton. Since it gained a proton, it accepted a proton. That makes this a base in this equation, and that means the other thing has to be an acid. And if I compare my acid, H3O+ compared to H2O has lost a proton. It has donated a proton, so that makes sense as well. In this next equation, this is where things get a little bit more complicated when we look at polyatomic ions. So you have to be able to identify that NO3 is a polyatomic ion. In this case, HNO3, I'm not going to compare it to the H3O+ because they don't really have very much in common. Instead, I'm going to compare it to the NO3. So this HNO3 has lost a hydrogen, which means that this donated a hydrogen. So that makes this an acid. And you guys already know this. A polyatomic ion with the right number of hydrogens to balance out its charge makes it an acid. This H2O gains a proton. So when it accepts a proton, that makes it a base. And then in this very last equation, NH3, it doesn't make sense to compare that to OH because that O isn't going to get traded back and forth between them. We're only looking for something that's similar to NH3. The thing on the right side that's similar to NH3 is NH4. So that gained a proton. Since it gained a proton, it accepted a proton, that makes this a base. And this makes sense too in the real world. Ammonia is very, very basic. H2O+ compared to OH, if we compare these two like things, it turns out that this H2O has lost a proton. So when it loses a proton, it donates a proton. That makes this an acid in this case. So you can see, depending on the equation, H2O could be a base or it could be an acid. So you really just have to take it one step at a time and see what happens to it. If it goes from H2O to OH, that's always going to be an acid. If it goes from H2O to H3O+, that's always going to be a base.